Let's look at another example of transportation model. We have three reservoirs with daily supplies of 15, 20, and 25 million liters of water respectively. On each day, we must supply four cities A, B, C, and D whose demands are 8, 10, 12, and 15 million liters respectively. The cost of pumping in rupees per million liter has been given to us. So for pumping the water from reservoir R1 to city A, the cost is rupees 2 per million liter, while from reservoir R1 to city B, the cost of pumping is rupees 3, and so on. We have been given the cost from each of the reservoirs to each of the cities. Now we are being asked to use the transportation algorithm to determine the cheapest pumping schedule if excess water can be disposed of at no extra cost. So let us understand this example in more detail. So we have been given that there are three reservoirs with a supply capacity of 15, 20, and 25 million liters of water. So let's say the first reservoir R1 is located here. So this is R1, and R1 has a supply capacity of 15 million liters of water per day. So we'll express all the numbers in million liters. So here the supply capacity is 15. Now let's say the second reservoir is here. So this is R2, and we have been given that the supply capacity for R2 is 20 million liters per day. So supply capacity is 20, and the third one is here, and the supply capacity is 25 million liters of water per day. So 25. So basically there are these three reservoirs who have the capability to supply water to different cities. Now there are four cities A, B, C, and D who have a demand for water. So let's place these four cities on this map along with their individual demands. So let's say city A is here, and A has a demand of 8 million liters per day. B is here, having a demand of 10 million liters per day. C is here, having a demand of 12 million liters per day. And D is here, having a demand of 15 million liters per day. Now, we have also been given that each of these reservoirs can supply the water to any of these cities. However, the cost of pumping water from each of these reservoirs to each of these cities is different and has been given in this matrix. So for pumping 1 million liter of water from reservoir R1 to city A, the cost is 2 rupees. This is rupees 2 per million liter. Similarly, For pumping water from reservoir R1 to city B, the cost is 3 rupees per million liter. From R1 to C, it is 4 rupees per million liter. And from R1 to D, the cost is 5 rupees per million liter. Similarly, from R2 to A, the cost is 3 rupees per million liter. From R2 to B, 2 rupees per million liter. From R2 to C, 5 rupees per million liter, and from R2 to D, 2 rupees per million liter. And similarly, we have also been given the cost of pumping from R3 to these 4 cities. So as you can see, each of these cities has multiple options of satisfying their demand using the water pumped from any of these reservoirs. However, there is a cost associated with each of the reservoirs pumping water to each of these cities, and that is varying by each of the reservoirs. So we have to now find out the cheapest pumping schedule using the transportation algorithm. So let's see how we can use transportation model to find a solution for this problem. So the first step in solving the transportation model is formulation of transportation table. In this step, we have to express the supply from origins, requirements at destination, and the cost of shipping from origin to destination in the form of a matrix. So let's try to create that matrix for the example. So on the left hand side, we'll place the reservoirs R1, R2 and R3, and on the right hand side we'll place the supply capacity, which is 15, 20 and 25. The supply capacity is in million liters. On the top we'll place the cities, so A, B, C and D, and at the bottom we'll have the demand at each of these cities, which is 8, 10, 12 and 15 million liters per day. Now in the center we'll place the cost of pumping from the reservoirs to the cities in rupees per million liter. So 2, 3, 4, 5, 3, 2, 5, 2, 4, 1, 2 and 3. So this is our transportation table. Now once we have formulated the transportation table, a check needs to be done to find out if the total supply and demand are equal. If yes, the problem is said to be balanced, and if not, a dummy origin or destination is added to balance the supply and demand. So let's first add up the supply. So 15 plus 20 is 35. 35 plus 25 is 60. Now let's add up the demand. So 8 plus 10 is 18. 18 plus 12 is 30. And 30 plus 15 is 45. So the total supply is 60 while the total demand is 45. So this means that the total supply is more than the total demand. Now, one of the assumptions for using the transportation model is that the total quantity of the item available at different sources should be equal to the total requirement at different destinations. So that assumption is not true in this case. So in order to use the transportation model, we'll have to make the supply and demand equal to each other. So what we can do is add another source of demand, which is like a dummy source of demand. And for that source of demand, we'll have the demand equal to the differential between the total supply and total demand, which is 15. So let's add another column here. So let's call this column as E, which has a demand of 15. And let's place the supply here as it was before. So 15, 20, and 25. Now this dummy source of demand will receive the excess water capacity, which is 15 million liters of water. Now this 15 million liters of water will not be shipped anywhere or will not be pumped anywhere because this is a dummy source of demand. And we have already been given in the example that the excess water can be disposed of at no extra cost. So we are disposing of the excess water, so there is no pumping cost for this differential of 15 million liters of water. So we'll put the cost of pumping as 0. So now let's add up the total demand and supply. So the total supply is 15 plus 20, which is 35, plus 25, which is 60, and the total demand 8 plus 10 is 18, plus 12 is 30, plus 15 is 45, plus 15 is 60. So now the total demand is equal to the total supply, which is equal to 60. And so now we can use the transportation model to solve this problem. Now the next step is to find out the basic initial feasible solution for this transportation table. Let's use the Vogel's approximation method to find out the basic initial feasible solution. Now the first step in Vogel's approximation method is to calculate the difference between two minimum elements for each row and each column. So let's go row wise first. So for the first row, the lowest cost is 0 and the second lowest is 2. So the difference is 2 minus 0, which is 2. For the second row, again the difference is 2 minus 0, which is 2. For the third row, the lowest is 0 and the next lowest is 1. So the difference is 1 minus 0, which is 1. Now for the columns, for the first column, lowest is 2 and the next lowest is 3. So the difference is 3 minus 2, which is 1. For the second column, lowest is 1, next lowest is 2. So 2 minus 1, which is 1. For the third column, lowest is 2 and the next lowest is 4. So 4 minus 2 is 2. For the fourth column, lowest is 2, next lowest is 3. So 3 minus 2 is 1. And for the fifth column, 0 minus 0, which is 0. Now the next step is to select the row or column with the largest difference. So we have a tie here between R1, R2 and C. So between these three, let's find out which selection will give us the maximum benefit. By maximum benefit, I mean which has the cell with the lowest cost, and if there is a tie again between the cost, then which of them will allow us to allocate the maximum. So for R1 and R2, the lowest cost is 0. while for C, the lowest cost is 2. So let's shortlist R1 and R2 first because they provide us the lowest cost of 0. Now between these two, let's find out which one gives us more allocation capability. So E has a demand of 15, R1 and R2 have a supply capacity of 15 and 20 respectively. So the maximum we can allocate to either R1 and R2 is 15. So there is a tie. So let's take any one of these arbitrarily. So let me take R1 first. Now after selecting the row or column, the next step is to allocate the maximum number of units to the square with the minimum cost in the selected row or column. So that square is R1E. Now let's evaluate the supply and demand situation. So E has a demand of 15 while R1 has a supply capacity of 15. So the maximum we can allocate here is 15. Now with this allocation, the entire demand at E has been met, so the remaining demand is 0. And also the entire supply capacity at R1 has been exhausted, so the remaining supply capacity is 0. Now since the entire demand at E has been exhausted, let's cross off the remaining boxes for city E, indicating that they are no longer required to be allocated. Also, the entire supply capacity at R1 has been exhausted. So let's cross off the remaining boxes for R1, indicating that they are no longer available for any further allocation. Now let's redetermine the row and column differences. The first row has been completely allocated, so we'll skip it. For the second row, the lowest is 2 and the next lowest is also 2. So the difference here is 0. Now here I took the lowest and the next lowest as 2 and 2 and not 2 and 3 because the main criteria of finding the lowest two elements is to find out that if we miss one of the cells which has the lowest cost and then we have to move to the next cell which has the next lowest cost, then how much is the penalty? So in this case, if we miss one of these cells, then the next cell that is available also has the same cost. So basically the penalty is 0. Now let's move to the third row. So the lowest is 1 and the next lowest is 2. So the difference is 1. Now let's move to the columns. So for the first column, 4 minus 3, 1. For the second column, 2 minus 1, which is 1. For the third column, 5 minus 2, which is 3. Fourth column, 3 minus 2, which is 1. And fifth column has been completely allocated, so we'll skip it. Now the next step is to select the row or column with the largest difference. So let's select column C. Now the next step is to allocate the maximum number of units to the square with the minimum cost in the selected row or column. So the square with the minimum cost in column C is R3C with the cost of 2. So let's evaluate the supply and demand situation for this square. C has a demand of 12 units while R3 has a supply capacity of 25 units. So the maximum we can allocate to this square is 12. Now with this allocation, the entire demand at C has been met and the supply remaining at R3 is now 25 minus 12, which is 13. Also, since the entire demand at C has been met, let's cross off the remaining boxes indicating that they are no longer required to be allocated. Now let's redetermine the row and column differences for each row and each column. Let's skip the first row as it has been completely allocated. For the second row, the lowest is 2 and the next lowest is also 2, so the difference is 0. For the third row, the lowest is 1 and the next lowest is 3, So the difference is 3 minus 1, which is 2. For the first column, 4 minus 3, which is 1. For the second column, 2 minus 1, which is 1. Third column we can skip. Fourth column, 3 minus 2, which is 1. And we can skip the fifth column. Now we have to select the row or column with the largest difference. So let's select the third row. Now we have to allocate the maximum number of units to the square with the minimum cost in the selected row or column. So that square is R3B. So let's evaluate the supply demand situation here for this square. B has a demand of 10 units while R3 has a supply capacity of 13 units. So the maximum that can be allocated here is 10. So with this allocation, the remaining demand at B becomes 0, while the remaining supply capacity at R3 becomes 3. Now since the entire demand at B has been met, let's cross off the remaining boxes indicating that they are no longer required to be allocated. Now let's redetermine the row and column differences for each row and each column. Let's skip the first row as it is completely allocated. For the second row, lowest is 2 and the next lowest is 3. So difference is 3 minus 2, which is 1. For the third row, lowest is 3, next lowest is 4. So the difference is 1. I think I missed circling this one, so let me do that. Okay. Now let's proceed to the columns. So first column, 4 minus 3, 1. Second column we can skip. Third column we can skip. Fourth column, 3 minus 2, 1. And fifth column we can skip. Now we have a tie between R2, R3, column A and column D. So let's try to find out which allocation will give us the maximum benefit. So of course, D and R2 will give us the lowest cost, which is 2 units. So let's select R2 arbitrarily. So let's try to allocate the maximum to R2D. So the demand at D is 15 units while R2 has a supply capacity of 20 units. So the maximum we can allocate is 15. So with this allocation, the entire demand at D has been met, while the supply capacity at R2 is now 20 minus 15, which is 5. Now let's cross off the remaining boxes at D as the entire demand for D has been met and the remaining boxes are no longer required to be allocated. So now we only have 2 squares remaining to be allocated, R2A and R3A. So let's select R2A as it has the lower cost between the two. Now let's evaluate the supply and demand situation. So R2 has a supply capacity of 5 while A has a demand of 8. So the maximum that can be allocated is 5 units. So with this allocation, the entire supply capacity at R2 has been exhausted and the demand remaining at A is now 8 minus 5, which is 3. Now since the entire supply capacity at R2 has been exhausted, all the boxes should either be allocated or crossed off, and as we can see, they are either crossed off or allocated. So now let's move to the last square for allocation, which is R3A. A has a demand of 3 while R3 has a supply capacity of 3 as well. So the maximum that can be allocated is 3 units here. So with this allocation, the entire demand at A has been met and also the entire supply capacity at R3 has been exhausted. So with this allocation, all the supply and demand has been allocated, and this allocation forms the basic initial feasible solution. So let's find out the total cost of transportation that we have achieved using the Vogel's approximation method. So the total cost will be the multiplication of the unit cost and the number of units pumped or shipped. So 15 multiplied by 0 plus 5 multiplied by 3 plus 15 multiplied by 2 plus 3 multiplied by 4 plus 10 multiplied by 1 plus 12 multiplied by 2 So this is 0 plus 15 plus 30 plus 12 plus 10 plus 24. So 15 plus 30 45 plus 12 57 plus 10 67 plus 24 is 91 rupees. So 91 rupees is the total cost of transportation based on the initial basic feasible solution that we have achieved using the Vogel's approximation method. So this is a feasible solution, which means that we can use these allocations to pump the water from these reservoirs to these cities without violating the supply and demand conditions. However, this may or may not be the optimal solution. That is, this 91 rupees may or may not be the lowest cost. So next we'll proceed to find out if this is an optimal solution or not. And if it is not, then we'll further try to improve it to achieve the optimal solution for this problem. So this is the basic initial feasible solution that we have achieved in the previous step. Now we have to find out if this solution is the optimal solution or not. So in order to find that out, we'll have to perform an optimality test on this basic initial feasible solution. However, before we proceed with the optimality test, we have to first find out if this solution is acceptable to proceed with the optimality test or not. And the optimality test can be performed only if this solution meets the acceptability criteria. The first criteria for acceptability is that the number of allocations should be equal to m plus n minus 1. Here m is the number of rows, n is the number of columns. So in our case, m is 3 and n is 5. So this becomes 3 plus 5, 8 minus 1, which is 7. Now let's calculate the number of allocations. So we have 1, 2, 3, 4, 5 and 6. So here the number of allocations is 6, and this is not equal to m plus n minus 1. So this is a case of degeneracy, and this solution is known as a degenerate solution. So what is a degenerate solution? Degenerate solution is a solution where the number of stone squares, or the squares which have allocations, is less than m plus n minus 1. A degenerate solution will create complications since the row and column values of all the water squares cannot be calculated. So these type of degenerate solutions can be resolved by making use of an infinitely small quantity, which is almost close to a zero, denoted by the Greek letter epsilon. To one or more water square, and treating that water square as a stone square. And since the value of epsilon is considered so small, it should not have any impact on the supply and demand constraints that we have been given. And the value of epsilon for all calculation purposes should be assumed to be 0. Now epsilon should be assigned to an independent water square, that is a water square from which a closed path cannot be formed. So for example, we can't assign that epsilon to this square R2B, because from here then we can easily create a closed loop, which will be R2B, R2A, R3A, R3B, and then back to R2B. So this should not be the case. Also, in case there are more than one independent water squares, epsilon should be assigned to the one which has the minimum per unit transportation cost. So let's first try the squares which have the minimum transportation cost, which is R2E and R3E. Let's see if these are in independent positions. So from R to E, I don't think we can create a closed path. So this is an independent position. And R3E is also in an independent position, as we cannot create a closed path. So let's choose R2E and create the stone square out of this water square. So let's assign this a value of epsilon. So now with this allocation, our number of allocations become 1, 2, 3, 4, 5, 6, and 7. So this first condition is met. And the second condition is that these allocations should be in independent positions. This means that you should not be able to form a closed path for any of the allocated cells. So as you can see, all the allocations are in independent positions. So the second condition is also met here. So now let's proceed with the optimality test. Now the basic fundamental of the optimality test is that we have to evaluate each and every water square, that is the squares without any allocations, to find out if an allocation was made to those water squares, would there be any possible reduction in the total transportation cost. So in this case, we'll use the stepping stone method to perform the optimality test. And in the stepping stone method, basically the fundamental is that for each and every water square, we'll create a closed path and we'll find out the net cost change for the water square, which eventually will give us an analysis whether that water square is capable of giving us any reduction in total cost or not. So the first step in stepping stone method is to proceed row by row and select a water square. Then the next step is to establish a closed path using rectilinear motions, that is moving horizontally and vertically only, starting from the selected water square via the stone squares and then back to the same water square. A right angle turn is made only at the stone square, even though the path may skip over stone and water squares. So let's first select the first water square, which is R1A. So R1A. Let's formulate the closed path. So R1A to R1E to R2E to R2A and then back to R1A. So R1A to R1E to R2E to R2A and then back to R1A. The next step is to assign alternate plus and minus sign on the closed path, starting with a plus sign on the water square. So basically why we are doing is that because we want to ensure that we don't violate the supply and demand constraints. So alternate plus minus sign. So starting with the water square, because we want to allocate something to this water square and then find out if it helps in the total cost or not. So first is plus, then minus, plus, and then minus. The next step is to calculate the net cost change for the closed path. The net cost change is obtained by summing up the unit cost of each cell. So now we have to replace these with the values of the unit cost. So R1A, the unit cost is 2 minus R1E is 0 plus R2E is also 0 minus R2A is 3. So this is equal to 2 minus 3, which is minus 1. Now let's move to the next water square, which is R1B. For R1B, the closed path is a little complicated. So from R1B, we can go to R3B, then to R3A, then to R2A, then to R2E, then to R1E, and then back to R1B. Let me draw this one for you. So starting is here, we come down, then we go to the left to R3A, then to R2A, then from here to R2E, then from here to R1E, and then from R1E back to R1B. So let's note this down. So R1B to R3B, to R3A, to R2A, to R2E, to R1E, and then back to R1B. Now we have to put alternate plus minus signs, starting with a plus sign from the water square. So plus, minus, plus, minus, plus, and minus. Now we have to fill in the values of the cost for each of these squares. So R1B is 3, R3B is 1, R3A is 4, R2A is 3, R2E is 0, R1E is 0. So 3 minus 1 is 2, 2 plus 4 is 6, 6 minus 3 is 3. Now let's move to the next water square, which is R1C. Let me first erase this closed loop that I had created to avoid any confusion. So the next water square is R1C. Let's try to formulate a closed loop for this water square. For this one also we'll have a similar closed loop as the previous one, which will be from R1C to R3C to R3A to R2A to R2E to R1E, and then back to R1C. So let's note this down. Now after finding the net cost change values for all the water squares, the next step is to evaluate the solution for optimality by observing the sign of the net cost change. If any of the net cost change values has a negative sign, then that means that a cost reduction can be made by making allocation to that water square. What that means is that the solution that we are evaluating is not yet optimal. So let's see if we have a negative net cost change value. So this is a negative net cost change value, then again we have another one, and that's it. So we have two squares R3E and R1A with a negative net cost change value. Since we have a tie and the value is -1 for both these squares, what this means is that whichever square we choose, the cost is going to be reduced by 1 unit. So now we have to compare which square has the capability to allocate more units to it, because that square will then give us more savings. So let's evaluate R3E and R1A. So R1A and R3E. So for R1A, the closed loop is R2A, R2E, R1E, and R1A plus minus plus minus. And for R3E, the closed loop is R3E to R3A, R2A, R2E, and then back to R3E, plus minus plus minus. So the maximum that we can allocate to a water square is the minimum at the squares with the negative sign. So in case of R1A, the minimum between 15 and 5 is 5. So we can allocate 5 units to R1A. Whereas in case of R3E, the minimum value between 3 and epsilon is epsilon, which is very close to 0. So between 5 and epsilon, 5 is greater. So we have a potential of higher savings in case of R1A. So let's choose R1A. So now we have to subtract the smallest of the figures from each square at the negative sign on the closed path and add it to each square at the positive sign on the closed path. So 5 is the allocation, so we can add 5 here, subtract 5, then add 5. So 5 plus epsilon is 5, as epsilon is very close to 0. So this is 5, and subtract 5, so 15 minus 5 is 10. So this becomes our new solution. Let me clean this up and show the solution that we have obtained after this iteration. So this is the solution that we have obtained after the first iteration. Let's find out the total cost. So 5 multiplied by 2 plus 10 multiplied by 0 plus 15 multiplied by 2 plus 5 multiplied by 0 plus 3 multiplied by 4 plus 10 multiplied by 1 plus 12 multiplied by 2. So this is 10 plus 0 plus 30 plus 0 plus 12 plus 10 plus 24. So 10 plus 30 is 40 plus 12 52 plus 10 62 plus 24 is 86. So 86 rupees is the transportation cost. So the previous solution that we had gave us a total transportation cost of 91 rupees. So we have reduced the transportation cost by 5 rupees here after the first iteration. Now let's find out if this is the optimal solution. Now before we proceed with the optimality test, we have to first find out if this solution is acceptable to proceed with the optimality test or not. So the first condition is that the number of allocations should be equal to m plus n minus 1. Now m plus n minus 1 here is 3 plus 5 minus 1, which is 3 plus 5 is 8, minus 1 is 7. Now let's count the number of allocations. So 1, 2, 3, 4, 5, 6, 7. So the number of allocations is equal to m plus n minus 1. So the first condition is met. Now the next condition is that the allocations should be in independent positions. That means that you should not be able to form a closed loop for any of the allocated squares. So if you observe, you'll find that all the allocations are in independent positions. So this solution is acceptable to proceed with the optimality test. Now one very important observation here is that after the first iteration, the solution that we got is not a degenerate solution. So let's recall what happened here. So earlier, the basic feasible solution had no allocation for R1A, it had an allocation for R2A, and there was no allocation for R2E. And because of that, the number of allocations was coming to 6, while m plus n minus 1 is 7. Now after the first iteration, what has happened is this one allocation at R2A has been removed, and there are two allocations which have been placed. One is at R1A and the other one is at R2E. Now these two are 5 and 5, which is 10. So where has this 10 come from? So earlier the allocation was at R2A, which was 5. So that 5 got moved, and R1E had 15, so it got reduced by 5. So that is how we have two allocations now at R1A and R2E. And the number of allocations is now equal to m plus n minus 1. So let's now proceed with the optimality test using the stepping stone method. So again, in the optimality test, we have to evaluate each and every water square to find out if it has a potential to give us more savings. So the first water square is R1B. Let's form a closed loop for R1B. So the closed loop can be R1B to R3B to R3A to R1A and then back to R1B. So let's note this down. So R1B to R3B to R3A to R1A. Now let's assign alternate plus minus signs. So starting with plus sign at the water square, then minus, then plus, then minus. Now let's fill in the values of the unit cost. 3 minus 1 plus 4 minus 2. So this is 3 minus 1 is 2, 2 plus 4 is 6, 6 minus 2 is 4. So now after we have calculated the net cost change value for all the water squares, the next step is to evaluate the solution for optimality by observing the sign of the net cost change. So in our case, we have two squares with a negative net cost change. One is this, the other is this one here. So R3E and R3D. So what this means is that the solution that we evaluated just now is not the optimal solution and still has some scope of improvement. So next we'll try to improve this solution and iterate towards optimality. So for iterating toward optimality, we have to select the water square with the largest negative net cost change value. So here we have square R3E with the highest negative net cost change value. So we'll select this square and try to make some improvements. So let me create a closed loop for this square R3E. R3E to R1E to R1A to R3A and then back to R3E, and alternate plus minus sign. So plus, minus, plus, minus. Now we have to subtract the smallest of the figures from each square at the negative sign on the closed path and add it to each square at the positive sign on the path. So out of the two squares with negative sign, the smallest allocation is 3. So we'll subtract 3 and add 3. First let's add 3 here. Subtract 3, so this becomes 7. Add 3, so this becomes 8. And subtract 3, so this becomes 0. So this is our new solution that we have obtained after the second iteration. Let me clean this up and write the new allocations that we have obtained. So let's calculate the total cost obtained by this solution. So 8 multiplied by 2 plus 7 multiplied by 0 plus 15 multiplied by 2 plus 5 multiplied by 0 plus 10 multiplied by 1 plus 12 multiplied by 2 plus 3 multiplied by 0. 16 plus 0 plus 30 plus 0 plus 10 plus 24 plus 0. So 16 plus 30 is 46. 46 plus 10 is 56. 56 plus 4 is 60 plus 20 is 80. So 80 rupees is the new transportation cost which we have obtained after the second iteration. Now the cost that we had obtained after the previous iteration was 86 rupees. So we have further improved the transportation cost by 6 rupees. Now let's find out if this solution is optimal or not. So before proceeding with the optimality test, we have to first find out if this solution is acceptable to proceed with optimality test or not. So the first condition is that the number of allocations should be equal to m plus n minus 1. Now in our case, m plus n minus 1 is 3 plus 5 minus 1, 8 minus 1 is 7. And the number of allocations is 1, 2, 3, 4, 5, 6, 7. So the first condition is met. The second condition is that all the allocations should be in independent positions. And if you observe, you'll find that we cannot create a closed loop for any of the stone squares, which means that these are in independent positions. So now let's proceed with the optimality test. We'll use the stepping stone method for checking the optimality. So the first water square is R1B. So the closed loop can be R1B to R1E to R3E to R3B and then back to R1B. So R1B to R1E to R3E to R3B. Now let's assign alternate plus minus signs. So minus, plus, minus. And let's now fill in the value of unit cost. So R1B is 3 minus R1E is 0 plus R3E is 0 minus R3B is 1. So 3 minus 1 is 2. So now the next step is to evaluate the sign of the net cost change value. So all the net cost change values are positive, indicating that if we make any allocation to any of these water squares, then our cost is going to increase. And we don't want to increase the cost, we want to reduce the cost. So basically we can't reduce the cost any further, which means that this solution that we have, which gives us a total cost of 80 rupees, is the optimal solution. So this was a pretty long solution. However, if you observe, this example had multiple cases embedded within it. The first being that this was an unbalanced transportation problem, so we had to add a dummy source of demand. And then this also had a case of degeneracy, so we had to add epsilon as one of the allocations.